The pilot of this supersonic jet is lining up to land on the flight deck of an aircraft carrier. The entire deck is about twice the length of a Formula One pit lane. The 23-ton plane must land in half that length, at 240 kilometers per hour. There is little room for error. The deck is noisy and crowded. Planes are landing, being serviced, refueled, rearmed, and taking off all the time. Amid the terrifying noise and mesmerizing action, everything is carefully choreographed by the carrier's control tower. The flight deck of a battle-ready aircraft carrier has been called the most dangerous place on Earth. Some reckon this is just as dangerous. A Formula One pit lane is lined with fuel, tyres, equipment, and filled with people. It is dangerous because no one is in overall charge. Each team brings its car in when race strategy suits it. Sometimes several cars and several pit crews are in the lane together.
It takes 19 people over 7.5 seconds to make a perfect pit stop, and each of those 19 people has to do it right. If one of the links in the 19-link chain is a bit rusty, then you've lost 10 seconds, you've lost the lead, you've lost the race.
It's choreographed, literally, just like something you'll see on the stage. Everybody knows exactly what he's got to do, when he's got to do it, how he's got to do it, and they practice, practice, practice until they are absolutely right.
Pit stop strategy involves wrong footing, outwitting, or simply outpacing the opposition. Rather than keeping everyone informed, as on the aircraft carrier, the trick is to keep it secret from the other teams. With engines running and cars screaming by on the track, it's impossible to hear or talk. Aircraft carriers bristle with electronic communication. Down on the noisy flight deck, these are unreliable. Here, hand signals are king. On this billion-dollar deck, surrounded by cutting-edge electronic communication, nothing is as safe as clear, simple hand signals. Hand signals run pit stops too. Braking point for driver. The jacks come in. 3 men change each wheel. Wheel nut secured, mechanics give clear hand signals. Jacks are lowered and removed. Refueling takes the longest. The so-called lollipop rises. The car is gone. Simple signals work best in noisy, stressful environments. This FA-18 Hornet is preparing to fly. It's been hooked up to the steam catapult. Throttles are set to take off. The pilot signals his hands are off flight controls. His launch is remote controlled by the catapult officer, the shooter.
Wind intervals, checkers, thumbs, head steady. Fire. Goodbye.
Once airborne, the pilot takes control.
Fans out, thumbs up, winds are good.
This is Formula One's version of the carrier's shooters. They are electronics engineers. They have invented computer software called launch control. On the starting grid, drivers just sit back and enjoy the ride.
It's a great acceleration, actually. It's a big kick. You know, as soon as it goes, it really, you know, all the way through the start into the first corner, the acceleration is, you know, it never stops.
Launch control ends the first time the throttle is lifted. So by the first corner of the race, the driver is back in control. Just like the pilot in the Hornet, once airborne, he takes control.
Launch control is an interaction between engine, clutch, engine management system, in order to automatically do the best start possible. The system operates on its own. It manages power transferred to the wheels by the clutch in a way that you have maximum acceleration.
So computers launch cars from the grid better than drivers.
We are watching an engineered start. There are many issues to deal with, and the driver is quite busy in this early phase of the race. So I think it's a support the driver really welcomes.
Launch control, in my personal opinion, putting my head on the chopping block, is a total load of nonsense. And Marianne Tyson is absolutely right. The engineers do the starts, because I'll show you how they start in the cockpit. Boom, they take the finger off a button. That's all the driver does, and the foot's flat on the floor. So what input does the driver have on the start? Steering the car, and that's it.
In Nigel Mansell's day, in the 1990s, drivers managed the starts. Spectacular, but burning rubber is wasted energy. Today, smooth electronic launch control is one example of how the role of the Formula One driver is being diminished. They are no longer alone in their cockpits. In Formula One motor racing, the driver was once the master. Now, he is no longer alone in his cockpit. A modern racing car is not driven by one man.
In Formula One, if you don't have everything, you don't win. You need to have the best car, you need to have, the best engineer, the best everything. And, that's what it takes to win.
Montoya's car is made by an enormous team. Designers, engineers, aerodynamicists and mechanics work together to produce the car at the Williams team headquarters.
Formula One is a team sport, and it takes a team to win. It's not only the chassis, it's not only the engine, it's not only the driver. It takes that and the tires as well. When all four are put together in the right way, you're going to win.
Starting.
Winning in Formula One is a science. Whether racing or testing, every move a driver makes with his car is monitored and recorded. It's called data acquisition, telemetry.
Telemetry has become a vital tool in Formula One. You cannot live without it. Telemetry is the only way to acquire data while the car is running on the track, and you need lots of data.
Lots of data is picked up from telemetric sensors located all over the car. They measure engine revs, oil pressure, fuel flow, position of throttle, clutch temperature, exhaust temperature, timing of gear selection, suspension movement, G-force, and more. Data feeds through high-speed communication cables into two electronic control boxes. Encrypted data is sent by microwave link via the transmitter antenna. Out on the racetrack, the car is in constant touch with computers in the pits. Vital statistics of temperature and pressure are constantly monitored as the car races. Less vital data, used to calculate things like lateral acceleration, is transmitted once a lap.
We are observing and monitoring the engine throughout the race. As soon as an engine is started up, the engineers are watching telemetry data. And normally an engineer finds out that there's something going wrong before the driver feels it.
Back in the pit lane garage, computers download data directly from the car. Data is not just for engineers at the racetrack, it is also beamed back to headquarters. BMW in Germany and Williams in England.
The data acquisition and the sort of extent to which we record the performance of the car is pretty comprehensive. We have what seems like endless channels recording all sorts of parameters off the car, and we can sit down and interpret that data into more meaningful forms of information.
More meaningful information means forensically examining data for the most minute clue that will lead to tiny performance gains in future races. Today, software engineers outnumber mechanics at the trackside.
They're so glued to the telemetry now that even on the pit wall, in those stands they have, they can't even see the cars going past in the track. All they see are the screens in front of them. So their knowledge, their nutrients, if you like, for the way they think, are totally dependent on what the TV screens and the data channels are showing them.
There was a time when race engineers watched cars on tracks. They were glued to another method of data acquisition: the driver. His brain was the computer, and his mouth was the printout. The unanswerable question is, were the drivers better or just different?
When you see the Nürburgring, old circuit that they used to race on in the 1950s, 180 corners, I mean, Christ, how do these guys go around there? And they were different sorts of drivers, you know, and they were much more important in those days, the drivers, than they are now.
At the earliest Grand Prix races, there was no telemetry. Drivers just talked or complained about their car. It was fast, slow, understeered, oversteered, got a puncture, overheated, rattled to a stop, or crashed. It was as simple as that. On long Grand Prix, drivers in two-seater cars were accompanied by mechanics and equipment. Rules governed which tools could be used. Being heard above the din of unsilenced engines running at racetracks has always been difficult. Spectators could be bellowed at through megaphones. But drivers on the start line could hear little. A flag was one reliable way to signal a start. There were others. Drivers raced for hours with only the vaguest notion of their race position. There was little pit-to-car contact. One of the first to get organised was Mercedes team manager Alfred Neubauer. Impressed after seeing the communication of race teams in America, he imported their ideas. The Mercedes team became famous for their pit-to-car strategies. Drivers gained huge advantages from Neubauer's secret signals with flags, pit boards, and rather cryptic hand gestures. Alfred Neubauer is the European pioneer of race strategy, and the first to recognise the importance of knitting the driver into a team. The exact origin of command and control at racetracks is lost in the mists of time. There are plenty of likely models. The flagging of the Victorian railways, red for stop. The organisation of horse racing was an obvious model for car racing. Both have marshals and stewards. And this history survives in the modern language of Formula One, with phrases like parc fermé and paddock.
And in the paddock, discuss the current form. Always an interesting topic in motor racing.
For the next 40 years, pit boards and flags remained the only effective way to pass information to drivers on the racetrack. But in pit lanes, nothing had been done to improve communication. Coherent speech was impossible over engine noise. So Brabham owner, young Bernie Ecclestone, can barely hear his driver's complaint. James Hunt could be using carefully coded hand signals. In fact, he just needs cooling down. By the late 70s, Lotus's Colin Chapman, who was a pilot, was experimenting with aircraft headsets plugged into a modified driver's helmet. A small microphone and speakers were planted in the helmet. Though far from perfect, intercom communication beat some of the pit lane noise. Like all good ideas in Formula One, it was quickly adopted in other teams.
Getting quicker and quicker, we've got to do the same. I put 2.5 more gallons in, so you've got another 7 or 8 laps to go. That's all right, 2.5. We've raised the front ride height nearly half an inch. That's it, all done. Right.
Soon, everyone was sporting the latest must-have driver accessory, a pit lane intercom. It was only a short step to fitting radio sets to cars. The aerial on Ayrton Senna's Lotus is clearly visible just behind the rollover hoop.
Senna and then later on Schumacher start to talk a lot. They start to communicate the whole time with the engineers through the race. And then suddenly it was coming a very important tool, and we discuss a lot through the race, strategies, setup changes in the pit stop.
Talking on the radio is a huge asset. I mean, I liked it, but I'd only have certain people I'd talk to, because the last thing you want to do is have someone on the other end of the radio talking a load of nonsense. So you've got to have professional people there to help you and assist you doing your job. But sometimes when you're trying to make a decision about the tyres and you can see the lap time sort of, just tailing off a little bit, when the window is to come in and watching the competition behind or in front, watching the traffic, how quick you're catching it, and let's say you've got 3 or 4 cars in front by 6 seconds, the last thing you want to do is catch them up and be held up. But you want to catch them up to the latest point you can, and then come in. So talking on the radio and working all things out like that is very, very important.
By the end of the 1980s, all teams communicated directly with their drivers. They talked strategy as they raced. It didn't suit everybody.
It was, for many years, very difficult to communicate because about the noises, vibrations, the interference on a racetrack. You had possibilities to talk with the crew in the pits, but it was difficult to understand each other. You had ear protections in for the engine noise, so it was difficult to hear the speakers from the helmet. So the radio communication was, in all my 20 years I've been in, always a pain. It never really worked perfect.
By the mid-1980s, things had improved. This Star Wars-style graphic of the time attempted to explain the future. Pit-to-car radio was joined by control boxes wired up to engine sensors. Vital statistics were shot back to the pits to be stored for analysis. Race engineers spotting signs of engine wear or high oil consumption could radio the driver in time to avoid catastrophe.
Sometimes, the engineers have done in the past, even with myself, say, look, just drop the revs by 500 revs, just save the engine if you can, especially if we're in a good position, with winning the race.
Telemetry could be used strategically, especially in the gas-guzzling turbo years of the 1980s.
We had a lot of fuel problems years ago, especially with the turbo cars. We had to conserve fuel as well. Sometimes you had to turn the boost down. And one Pacific race, which was incredible, Patrick Head and I had a huge exchange on the radio because I was winning the race, and I did follow his direction. He told me to turn the boost way down. As I turned it down, and Keke Rosberg passed me, I was trying to keep up with Keke, and I was upset, and I was going balmy. When can I turn my boost up? When I can turn boost up? And later on in the race, when the engineers decided I had enough fuel to get to the end of the race, I could turn the boost up. We had the most fantastic race, and I ended up winning it.
So much of winning and losing is about the strategy. Who is making pit stops where? Are you going to run your car full of fuel and make fewer pit stops, or light on fuel so it's lighter and faster, but then have to make more pit stops? And are you actually going to change your strategy during the race, depending on what else is going on around?
By the 1990s, telemetry had become two-way. Cars like this 1993 Williams had bi-directional telemetry. The pit lane could send command signals directly to some components of the car.
The mixture of the engine, or maybe some settings of the electronics of the engine, could be altered, or maybe the strategy of the differential control could be altered, or maybe we could send a message to the driver which would come up on his screen and tell him something about his position in the race, or maybe something about a problem that we'd seen from the data coming to us on the car.
In 1993, amid fears that technology was making the sport robotic, two-way telemetry was banned. But inevitably, some teams were bending the rules. Secret computer code could be hidden within software running legitimate electronic functions.
Formula One is rightly regarded as the pinnacle of motorsport. It is the most technical version of motorsport. And you can't stop technology. It's like life. You can't stop it. It's going on all the time. You can't uninvent things that have already been invented.
F1's rule makers, the FIA, found it impossible to enforce the ban of driver aid electronics. Two-way telemetry was unbanned in 2002, opening the old arguments that Formula One drivers were in danger of being little more than highly paid machine minders.
He can override anything on that the bidirectional telemetry can do. He can press the buttons himself and change ignition maps and fuel maps and diff and all the rest of it. But the pit-to-car telemetry has reduced the workload that the driver has to do, so he can concentrate on driving and not playing around with a computer on his steering wheel.
A good driver with a sense of mechanical well-being, like Michael Schumacher, who is brilliant at it, like Nigel Mansell, who was extremely good at it, can add a considerable extra input to what the electronics tells the engineer.
Fundamentally, there is only one guy that's hanging onto that steering wheel or pressing the brake pedal, and really he is the guy that knows what the car's doing. And there's also elements as well that a driver can sense the behaviour of the car, and he will adjust his driving style accordingly. So that won't manifest itself in the data on the car because he is naturally driving around that characteristic in the car.
They have to understand the technology. They have to be able to use the electronics. So it's not true that that they are robots. Of course, they're not robots. It's just a different set of skills, or it's an overlapping but significantly different set of skills that are required now from the old age.
Williams drivers Montoya and Schumacher are patched into an electronic matrix monitoring all their moves. The role of the Formula One driver has probably changed forever. The question is, as technology advances further, how different will their cockpit role become? The answer might lie in the way that the cockpit has been developed to support modern fighter pilots. Technology is crowding the cockpit of the Formula One driver. It supports him while he concentrates on the battle to win. Much of this technology has come to motor racing from aerospace. To pilots of modern fighter aircraft, winning is a matter of life and death. But the conditions under which they operate are similar to racing drivers. This simulator for Eurofighter's active cockpit has taken some control away from pilots. It is designed to withhold information.
1, 2, go.
The idea is that hearing no news is good news, unless the pilot needs to know.
Close.
The philosophy is, if you don't need to know, I ain't going to tell you, because it's all working as you expect it to do. We have a set of design principles and philosophies that reinforce that. And That in itself has been possible through computers in the aeroplane.
Wing tank empty. Wing tank empty.
Fuel. Waypoints.
The computer talks to the pilot, and the man can talk back to the machine. Until something goes wrong.
Display stores.
The voice of the pilot is like an extra limb.
Voice in and voice out are the two real systems we have. My voice in to be a replacement for me taking my hands off the throttle and stick, which is important for controlling the airplanes, to take it off to select another function, another display, another radio frequency, many tasks. Tasks that I would describe as housekeeping tasks within the cockpit, done by voice.
Fuel low.
I can do something by voice and I can do something by hand at the same time.
Display warnings.
Increasing my productivity.
Most fighter pilots are likely to be male. Psychologists have found that they respond best to female voices.
Display engines.
Mother knows best. Especially if you're likely to die.
Pull up. Pull up.
Different levels of urgency come with the voice. You can hear her when she's really worried that you're about to hit the ground. She'll shout at you, pull up, pull up. Or when she's not too concerned but you're starting to run low on fuel, she'll give you a bingo fuel warning, an old code word for you're at a specific level of fuel. So the airplane's alive in terms of its response to you.
Transonic. Transonic.
The cockpit knows by what you're doing where it is, what phase of flight it's in. When the wheels are on the ground, and the airplane knows that, and the engines have just started, it knows that it must be going to taxi and take off next. So we give him information that are appropriate to those tasks. Once we get airborne, the undercarriage comes up. It gives me more information about navigation tasks. If I select a weapon or a target, it gives me combat task information.
Target kilo.
That's one of the ways we get around the problem of overloading the pilot with too much information available in the airplane.
Voice control and computers free pilots from all but their most crucial cockpit tasks: battle strategy and combat. Microprocessors made this possible. That was the idea at the heart of this car, the 1993 Williams FW15. It was designed to relieve the driver of as much cockpit management as possible, even gear changing.
The computers change all the gears up, all the 2 gears down, and if you call for a gear wrongly, if you say, I want to go from 6th to 2nd, and you do it at the wrong time, the computer says, oh, I'm not going to give you that, because the wheel sensor's telling me that you're doing 180 miles an hour, and to go into 2nd gear, you need to be doing 100 miles an hour. But don't worry, as soon as the wheel sensor slows down and tells us you're doing 100 miles an hour, automatically we'll change it instantly for you.
Mansell won in Formula One's most advanced car. Williams cars were the most technologically superior at the time. Having pioneered the semi-automatic electronic gearbox, they were going a step further with this: constantly variable transmission, CVT. A young and keen David Coulthard was the Williams test driver in 1993. No test bed is a substitute for shaking down the car with a test track drive. Constantly variable transmission is a perfect example of machines talking to machines. The engine is electronically linked by sensors to the gearbox. This keeps the engine speed within its peak power range. David Coulthard will not do any gear changing. The electronics do all the work for him.
We're working with the gearbox, and the driver is aware of constantly the RPM dropping and the car moving forward and back, and it's all very aggressive. But the feeling of the car now is, I'm very excited, because when I enter the corners, it's so smooth. We have none of the down changes to make, because the car is making the changes itself, and it proves that the machine is working better than man, because it can make smoother gear changes than I can.
Making machines that work better than man is technological progress for a pragmatic engineer like Patrick Head. The rule makers didn't see it like this.
We were banned from running it before it had even got to a motor race. I think there was, people running scared in advance. They just thought, oh, well, if it's going to make that car quicker, we'll agree to get it banned.
Less than a year later, at the end of the 1993 racing season, all driver aid electronics were banned. They were regarded as a threat to the battle between drivers. But even after the banning, rumours circulated about cheating, with secret illegal computer programs hidden deep within legitimate software. But banning technology in Formula One just invites engineers to think harder.
By banning things, all you do is redirect your known resource into another department and develop another technology.
Or go deeper into the existing technology, looking to gain tiny margins of performance.
It's really on the edge. You are constantly improving. You are trying to improve between every race, all the races. Every 2 weeks have something new. And at the same time, think about next year's engine, which has to be completely new, completely different again. So you are always pushing, always developing, never resting.
Never resting, Formula One engineers live in a culture of constant improvement. The potential for performance gain is often highest in aerodynamics or tyres. But on the grid, waiting to start, the engine is still the heart of a good car. In the past, engines were the highly visible mechanical heroes of Grand Prix cars. They were big, sexy, and the key to winning Grand Prix races. Like boxers talking tough before a fight, teams revelled in showing off their chunky new engines. That age is over. Today's modern Formula One cars are now conceived and built in enormous secrecy. Their engines are kept covered up.
You certainly want to keep a competitive advantage if you have one, and that's why we try to hide the secrets. If you see a naked engine, a good engine designer would see something and would learn something, even by only seeing the outer shape of the engine. And that's what we try to avoid.
This E41 engine from the 2000 Formula One season is the first that BMW developed for Williams.
The Formula One engine is dedicated to crank out as much power as possible and to last for a certain range, which is very short compared to a production engine. So if you had a Formula One engine in your road car, you had to replace it about 400 to 500 times to make the same mileage as with your conventional car.
The power generated from a road car engine is compromised by its need for reliability and longevity. A race car engine must be reliable, but it doesn't have to last very long. What counts is power.
The optimum Formula One engine is about maximum power and minimum weight and size in order to generate the optimum package car engine. So what we do is shrink everything, fight for every gram, every millimeter when designing each individual part, down to the smallest bolt.
Modern Formula One engines are all 3-litre V10s. They are 2/3 the size and less than half the weight of their road-going counterparts. Inside a Formula One crankcase, it's mechanical hell. Huge power is generated by moving the parts at 3 times the speed of a road car engine, around 18,000 revolutions per minute. Exhausts glow red hot. Massive forces are generated. Pistons experience 7,000 G, 7,000 times their own weight. Components like crankshaft and pistons are designed on the limit of their tolerance. Formula One engine designers build components light enough to achieve high revs and just strong enough not to break.
The crankshaft of the V10 engine is shorter than the one of the six-cylinder road car engine. It's less than 50% of weight of this one. And this shows what you have to take care of in order to achieve the high engine revs you need in Formula One. It's not just about crankshaft, it's about piston, it's about conrod, same issue. To go up in revs, you have to keep mass forces under control, which means to reduce weight to the absolute minimum, and by the same time increase strength of all the components. So we have a very light and small piston in our production engine already, which certainly is state of the art. But compared to the Formula One engine, you see the sleeves are much shorter again. It's much more refined. You try to take out every individual gram, try to shrink it by fractions of a millimeter in order to really get to the limit.
Shaving weight off or getting to the physical limit of the components is the secret of a winning engine, making it just strong enough to last the distance without blowing up.
It's almost a disposable product. Yes, at the end of doing 400 kilometres, the thing is pretty tired and a lot of components will be replaced. Some parts, major castings and things will be retained and freshened up, but a lot of components will be replaced. So in a way, you could also think of it the other way around. If your F1 engine could last you 1,000 kilometres, actually you'd be pretty annoyed because that meant you were carrying around a lot of excess in terms of probably weight, actually.
Reducing weight on a race engine means it's always close to its own destruction. It's all power, or no power.
The challenges facing an F1 designer at the moment really are all focused around power and more power. So in order to generate power, that basically means we've got to get more air into the engine. More air into the engine, because we've got a fixed capacity at 3 litres, essentially means more revolutions per minute. So we've just got to get the engine to spin faster. So all the challenges are focused around getting the revs up. So you'll hear people talking about, 17,000, 18,000 revs per minute, and it will just keep climbing.
Ferocious competition and the rules of Formula One means that the power produced between different teams' engines is relatively small. Here, at Ricardo Motorsport Engine Division, the details of managing engine airflow to find more power are mathematically analysed in a virtual world. Computational Fluid Dynamics, or CFD, is software developed for calculating aerodynamic equations. Colours represent different stages of the combustion process in an engine. The white dots are fuel droplets. CFD is used for searching out tiny power gains in components, like the airbox.
The figure on the top right is looking at the design of the airbox. The airflow is being driven into the engine by the forward motion of the car, but also underneath the engine is breathing, cylinder by cylinder is drawing on that air in the airbox. The natural tendency for the air would be, just through inertia, to effectively stick to the rear of that airbox, which means we tend to get more air towards the rear cylinders and less air towards the front. And by looking at this type of calculation, we can see where the air is trying to go, influence it through the various designs internally in that airbox. What we're trying to do is to get equal air to each cylinder. Then we can be sure that every single cylinder in the engine is producing all of the performance that it can.
Airflow calculations buried deep in computers are vital cogs in the vast machine that builds Formula One cars.
An F1 car is a system. You're relying on a number of actually quite complex systems of their own to sit and talk to each other and work together in harmony. So the closer those system designers and developers are together, gives you a much better chance of coming up with an integrated package which theoretically should perform better on the track.
Better performance on the track relies on huge resources off the track. Formula One is packed with the most advanced computers and electronic software, but the best computer is still the driver's brain. The question is, what is it best at? Grand Prix motor racing has come a long way from its beginnings. Sponsorship has made Formula One a $3 billion a year industry. Everything and everyone, whoever they are, is a branded product. These riches have bought teams access to technologies and materials associated with missile defense, medical research, and aerospace. So today's Formula One drivers need more than just skill and muscle power. They need to be an intelligent link in the chain. To get 36 hours of racing from 2 cars a year now needs the joined-up resources of hundreds of people in a factory. Formula One is a real team sport.
Formula One is a sport from 2 o'clock until 3:30 every other Sunday. All the other time, it's a business. And it is a business because you've got to get these vast sums of money in and because you're competitive. I mean, I always say that Formula One is the ultimate distillation of life because the rewards for success are higher, like Michael Schumacher, who's paid £50 million a year. The penalties for failure are greater, like Ayrton Senna, who was killed.
Spectators want to see cars battling wheel to wheel on racetracks. Critics complain that the cars can't do this because of their design. They say the technology that powers the sport has diminished the spectacle. These critics say, strip out all aerodynamic devices, take away the front wing, remove the rear wing, ban the underbody diffuser arrangements, take out all electronics. What we would end up with are the Coopers and Lotuses of the 1950s and 60s. A pre-sponsorship era when teams raced in their national colours. It simply wouldn't be Formula One. Today's Formula One is supposed to be led by technologists and engineers. Formula One showcases technological possibilities. Rules and restrictions just set new and bigger challenges for the technologists and managers running the teams. The role of today's Formula One driver is different, but he's still vital.
I think the driver is always going to be the defined limit of how far the car is going to go. It's up to the driver to set up the car with the engineers as comfortable as you can put it to go as fast as possible, you know, to find that new limit.
Complicated and difficult to understand. Critics accuse Formula One of being out of touch and irrelevant. They argue that it's become technically obscure and ask what use Formula One is.
Who cares what use it is? What use is football? What use is cricket? What use is lacrosse? What use is athletics? Formula One entertains people.
Ultimately, Formula One comes down to 2 guys going racing on Sunday afternoon 17 times a year and 500, 1,000 people behind each person, in effect. So there's this incredible contrast between NASA-like technology and this ridiculous human instinct to want to race cars on a Sunday afternoon.
For 30 years, one of Formula One's most successful teams has been run by Frank Williams. He understands how important Formula One really is.
I think if F1 were banned internationally for some terrible reason, it would disappear beneath the waves and speedily be forgotten, except for a few enthusiasts who'd have nostalgic memories, of course. But its contribution to the world order is minimal at best, except for the fun. And the fun. I hope it gives people around the world.